There is nothing more important than our children's health. Their development, happiness, and the future depend on how early we notice and respond to their needs. When something feels different, every moment matters. That's why early support can change a child's life. Some children experience the world in ways we don't immediately understand. Their senses and brains don't always connect in the usual way. This is autism, a lifelong condition that affects how they receive, communicate, and interact with others. It shapes how they speak, how they relate to people, how they manage sound and lights and emotions. It's not just a difference, it's a spectrum, with each child showing their own unique blend of challenges and strengths. In our country, 1 in every 68 children was diagnosed with autism in 2023. Across the MENA region, rates vary, but the need for better support is universal. Most autistic children are placed in schools that lack awareness and resources. As they grow up, many face unemployment and social isolation. Early diagnosis could change that, but it's often too slow, too late, and too subjective. Traditional diagnosis relies on long observation periods and limited clinical access. AI offers promise, but existing tools are narrow, missing the bigger picture. Autism shows up across behaviors, movement, speech, emotion. No single test can catch it all in one sitting, and the shortage of specialists makes this even harder. That's why we created Nabta, a smart multi-symptom assessment platform powered by 6 AI models that outperform existing tools. It provides affordable, accessible, and accurate evaluation to support effective and early diagnosis. Our system consists of 3 main modules designed to assist parents, doctors, and psychiatrists. The first module allows parents to upload various types of data which are processed by AI models to classify Autism Spectrum Disorder (ASD) and its severity. The system then generates a primary report offering parents a preliminary assessment. This primary report is then reviewed by an expert who validates the results and prepares the final report containing the complete assessment of the child. Psychiatrists can also review selected challenges and reports to enhance their diagnostic skills and experience in ASD assessment. These AI models are integrated into a user-friendly bilingual website. Together, our 6 models cover most symptoms observed in autistic children, enabling a truly comprehensive evaluation.
Our first model is designed to detect repetitive actions, which are also known as stereotypical behaviors. For training this model, we use 2 datasets, SSPD and ESPD. They both include 3 behavior types: arm flapping, head banging, and spinning. Our approach starts by detecting the child in the video, then estimating their body pose. After that, we use an action recognition model to classify the behavior. For child detection step, we use detector on 2, which works in 2 stages. In the first stage, it detects all objects in the frame, applies a convolutional neural network to classify them, and identify the child. In the second step, the child is segmented from the background to improve classification accuracy, and remove irrelevant background content to help the model focus better on the child's behavior. Next, we applied media pipe to extract 3D body landmarks from each video frame. In the final stage, we use a state-of-the-art model called Multi-Scale Vision Transformer to recognize stereotypical behaviors. Its architecture learns visual representation by gradually increasing channel resolution while reducing spatio-temporal resolution across stages. It's especially good at analyzing complex videos where small, quick behaviors like brief stemming needed to be detected precisely. Our study is the first to explore the use of multi-scale vision transformer for identifying ASD-related behaviors, and it clearly outperforms previous benchmarks. Our model achieved a groundbreaking accuracy of around 96% on the SSPD and ESPD datasets. Even when tested on different datasets by Wee et al., it still performed well, with 91% accuracy, proving its generalization ability. Even when the model has already demonstrated outstanding accuracy and generalizability across diverse datasets and environments, further improvements is still necessary. For future enhancement, we began implementing a multimodal training pipeline. Inspired by Deng et al., who adds language-assisted learning by feeding the model written definitions of behaviors from literature during training. We will extend this by integrating a video captioning module using the COG VLM2 alongside the multi-scale vision transformer. For the second model, we initially planned to implement eye contact detection using egocentric vision techniques. This relied on the Georgia Tech egocentric autism dataset, the only autism-specific egocentric dataset. However, due to regional and technical constraints, it wasn't possible for our context. We pivoted to an innovative webcam-based multi-symptom analysis system. In this setup, children interact with engaging autism-tailored cartoons, while the system passively runs in the background, analyzing a wide range of behavioral indicators in real time. This model is designed to capture behavioral, physiological, and emotional cues essential for ASD assessment. We start the model by analyzing emotion, attention to visual contents, and blinking rate. Recently, we added mouse anomalies and head movement stability, which provides a scalable and accessible solution that analyzes sensory, motor, and socio-emotional in real time. Unlike isolated feature systems, our pipeline integrates all markers into a unified analysis framework. To promote meaningful engagement, we integrated selected episodes from the PA Pro series, a show designed for autistic children. It addresses social anxiety, emotional understanding, and communication through storytelling and behavioral modeling. By embedding this content in our system and activating the camera in background, children interact naturally. Once the webcam is activated, frames are continuously captured and processed. We begin by detecting faces using retina face, which combines supervised and self-supervised learning for enhanced accuracy. Each detected face is then classified as either a child or an adult using a vision transformer. Next, media by face mesh is applied to extract 468 3D landmarks, enabling precise behavioral analysis. Blinking is measured using the eye aspect ratio derived from inner and outer vertical eyelid distances and eye widths. A blink is detected whenever the eye aspect ratio falls below a threshold of 0.45. Blinking rate is an important marker that correlates with sensory regulation and engagement, which are all critical factors when assessing ASD symptoms. Head orientation is estimated using key reference points extracted from the 3D facial landmark, specifically the nose tip, chin, and eye contours. From these, we compute the Euler angle, pitch, roll, and yaw, which represent the spatial orientation of the head. Head pose variability indicates attention or sensory regulation difficulties, providing a quantitative marker of head stability. To measure eye contact, we developed a multi-stage scoring system that integrates both iris position and head orientation data. Emotional states are analyzed using deep face, which extract feature using a convolutional neural network and compares them to pre-trained emotional templates. This emotional patterns helps identify moments of empathy and anxiety or enjoyment, which are crucial for understanding social and emotional processing. Then mouse posture is analyzed using mouse aspect ratio. This ratio compares the vertical opening of the mouse to the horizontal lip distance. A high mouse aspect ratio reflects open mouse posturing, often linked to neuromotor issues. Once the session ends, parents or clinician can access the analyzed recording and a comprehensive report for review. Beyond delivering immediate behavioral insight, this model also serves as a secure data collection tool for ongoing research, supporting the development of a scalable multimodal framework for early ASD detection and assessment. In addition to facial behavior analysis, we implemented a powerful eye contact and gaze estimation module as our third model. This model is inspired by a 2023 study which highlights that social visual behavior is central to understanding social cognitive processes in the complex context of autism therapy. However, collecting and analyzing gaze data manually is extremely time-consuming and effort-intensive for human coders. To address this, we used Gaze LLE, a state-of-the-art large-scale learned encoder recently honored with a badge of excellence at CVBR 2025. This advanced model allows us to move beyond eye tracking to assess complex social behaviors, such as mutual gaze when two individuals look directly to each other, and joint attention when multiple individuals focus on the same object or location. These delicate but crucial behaviors are essential for early ASD diagnosis, yet they are challenging for clinicians to measure manually because they happen quickly and are hard to notice. Our system automates this process in just a few minutes, giving clinicians a fast, objective, and highly valuable tool to support ASD assessment. Using Gaze LLE, which is a transformer-based gaze estimation framework optimized for low computational overhead and high flexibility, it has two main components. Its backbone is a self-supervised vision transformer trained with distillation with no labels on large-scale unlabeled datasets using constructive learning. It produces high-quality, dense scene representations. In this architecture, the encoder is frozen, its weight remains unchanged during training, and the output of the scene encoder is passed to a transformer-based gaze decoder. This model integrates head position embeddings post-encoding, which is an innovation over the traditional approach of integrating them pre-encoding. This design improves performance and allows GAS LLE to operate with only 2.8 million parameters, making it suitable for real-time deployment. Our full pipeline includes 3 pre-processing steps. The person is first detected in each frame using YOLO V8. Each detected person is passed through a vision transformer trained to classify them as child or adult. Only the child proceeds to the third step. The detected child is tracked using an intersection over union. Involves matching detected bounding boxes across frames based on their spatial overlap to maintain continuity. Additionally, identity matching refines tracking by comparing visual or motion features, ensuring consistent IDs even during occlusions or appearance changes. Then our gaze estimator is working to get the direction of gaze and the probability distribution of where the child is looking visualized as a heat map. Using the coordinates of gaze for both child and other people in the video, we apply advanced computer vision techniques to accurately detect mutual gaze and joint attention using density-based spatial clustering of application with noise algorithm. Both are well-established early indicators of social communicative development and are often diminished in children with ASD. This module enhances our system's ability to capture nuanced and often missed social behaviors, reinforcing its role as a key asset in autism evaluation and support.
Our fourth model focuses on integrating audio and visual data to support the assessment process. It analyzes the child's social interaction, language use, and repetitive routine, key indicators of autism that are often difficult to observe in standard assessment sessions. This model is based on a research paper published in 2024, which shows that in some cases, visual data alone fails to detect certain ASD-related behavior. However, when combined with audio, the classification accuracy improves significantly. In that paper, the researcher introduced the AVASD dataset, the largest dataset for autism behavior recognition to date. It is the first to include both social interaction behavior and repetitive behavior, making it a valuable resource for multimodal ASD assessment. All the categories in this dataset are essential for identifying ASD, such as non-typical language, self-injurious and aggressive behavior, and lack of responsiveness to variable interaction. The approach of this model involves several pre-processing steps. First, video frames are arranged into a 3x3 grid which serves as the visual input. For the audio, CONNET is used to generate a caption that describes the sound in the video, while the Whisper model produces a transcription of the spoken content. These outputs, along with the same behavior categories, are combined into instructor prompts. These prompts are then used to fine-tune the multimodal large language model LLaVA using LoRa technique, enabling multi-label classification for each video. After completing pre-processing, representation, and then structure prompt creation stages, we fine-tune the Barry-Jama 2 model from Google, a powerful vision language model that integrates both visual and texture understanding. Despite having only 3 billion parameters, it achieved comparable overall performance and outperformed LLaVA in several key categories on the AVASD dataset. The proposed pipeline achieved higher F1 score in several behavior categories compared to LLaVA ASD. However,
The fifth model uses graphomotor skills like writing, coloring, or drawing, often challenging for individuals with ASD. AI can be used here for analyzing child samples to assess task performance. Our model was trained on a dataset that includes around 1,000 images of both ASD and non-ASD children, with variability in age and severity. These children performed the 3 tasks, providing diverse samples, ensuring robust learning for our model. The models are trained to recognize patterns in coloring, drawing, and writing tasks, also to assess the severity of ASD when these patterns exist. Our method first uses binary classification to detect ASD likelihood in an image. If positive, a second model evaluates the severity. Our results are groundbreaking. MobileNet overperformed all models in ASD binary classification and severity prediction, achieving top accuracy with the fewest parameters. This makes it perfect for efficient real-world deployment.
Our system integrates the QChat-10, a streamlined parent-reported tool that screens for early autism signs by assisting behaviors like eye contact, gesture, and the response to names. Unlike basic ASD or non-ASD models, ours allows estimating severity, like mild, moderate, severe, giving clinicians deeper insights. The QChat-10 distills the original 25-question version into 10 critical items focusing on social, communication, attention, and sensory responses. Parents report the frequency of behaviors from pretend to play with children. We then combine this data with AI-driven behavior analysis using ensemble learning, ensuring caregiver input to enhance accuracy. To make model transparent, we used SHAP analysis to identify which behaviors most influence prediction. Top predictors were A6, B6, following gaze, A7, empathy, and A9 gestures. Frequency occurrence strongly correlated with ASD. Also A1, name response, A5, pretend play, also key but less likely. Other behaviors like eye contact, pointing, and the first words contribute but less weight. This clarity helps clinicians and parents understand why a prediction is made, building trust in the tool.
Our mission is not only to build and train AI models, but also to empower parents to easily assess and monitor their child's development from home, providing early indications that support timely intervention. To make this possible, we developed Nabta, a user-friendly bilingual website that integrates these AI models and offers seamless access for both caregivers and specialists. Parents can create accounts, add their children, test their children's behavior, and manage or update tests at any time, ensuring continuous monitoring and seamless user experience. Parents can remove tests or start new ones based on the specific symptoms they want to explore. Our platform Nabta incorporates the 6 AI-powered models that collectively detected around 16 autism-related behavioral symptoms, ensuring comprehensive and targeted coverage. When a test is selected, a guided video explains how to perform and upload it. Each AI model includes a specific instructional video, terms and conditions, and step-by-step guidance. Once the media is submitted, it is processed by the system and parents receive a notification to view the results on their personalized dashboard. The child's report includes detailed information about both the parent and the child, along with all associated tests. Each test section contains the uploaded media and the behaviors detected, such as arm flipping, head banging, or spinning in the stereotypical behaviors models, eye contact and gaze tracking, graphomotor patterns from drawing, writing, and coloring, and the social attention discourse. In addition, the report provides recommendations from specialists based on the child's assessment results. If parents choose the attention, emotion, and blinking analysis model, they are asked to select a video from a set of carefully curated educational and engagement clips, each chosen after extensive review. The system then requests webcam access, and once the session begins, it records and analyzes the child's reactions in real time. This approach helps ensure the child remains relaxed and behaves naturally while watching the video. After the session, parents receive a comprehensive report with insights into the detected and analyzed symptoms. On the specialist side, they can access reports for all assigned children and filter them by status as reviewed or unreviewed. They have the ability to modify or approve the preliminary assessment, and they can also add personalized suggestions and notes, which are then shared directly with parents or caregivers. Our goal isn't to replace clinicians, but to empower and support them. That is why we developed 2 dedicated modules, one for experts to manage and track patient data and another focused on training, designed to help junior clinicians enhance their diagnostic skills for more objective evaluations. The psychiatrist training module is specifically tailored to support psychiatry students in developing the expertise needed to become skilled professionals who can better guide families on their journey with autism spectrum disorder. This project has equipped us with a wealth of knowledge, exposing us to cutting-edge tools, advanced AI models, and state-of-the-art neural networks. Along the way, we explored powerful methods that not only helped us overcome challenges in this project, but also prepared us to solve complex problems in future endeavors. This project will empower parents by giving them the tools and systems they need to support their child's development and provide them with valuable insights to raise awareness. With access to this early information, parents are more likely to seek early intervention services, which can significantly improve their child's long-term outcomes.